Paper 2, tip number 7, organic molecules. Common question themes in recent paper 2s are all about recognizing homologous series, the idea of structural isomerism, then naming esters, recognizing and naming chloroalkanes. You'll usually find these questions placed between 30 to 36. The homologous series you'll be expected to recognize will be alkanes, alkenes, alcohols, carboxylic acids, and esters. So let's run through some basic ideas. We've got butane, an alkane, C4H10. Its structural formula would be CH3, CH2, CH2, CH3. So displaying that, CH3, CH2, CH2, CH3. Its molecular formula, C4H10. So this is a structural formula. This is the molecular formula. Because there are 4 carbons, the stem is bute. Because it's an alkane, the name ending is ane, ane. So butane. Bute for 4 carbons. Ane tells you it follows the general formula of an alkane. C4H10 is the result. The displayed formula or displayed structure shows all the bonds and the atoms and their positions. We would refer to that as a saturated molecule in that the carbon-carbon bonds are single bonds. So where there are carbon-carbon single bonds only, the molecule is referred to as saturated. If we now look at an alkene, propene, 3 carbons, hence propene, telling us it's got a carbon-carbon double bond. So 1 carbon-carbon double bond, which means it's referred to as unsaturated. How would we write the structural formula? CH3, CHCH2. CH3, CHCH2. Its molecular formula, C3H6. So this is an alkene. Alcohols contain the hydroxyl group OH. So a typical example, ethanol. Here is the structure you're expected to recognize. CH3, CH2, OH, the presence of the hydroxyl group. As the carbon-carbon bond is a single bond, it is saturated. Its molecular formula, C2H6O. Carboxylic acids contain the functional group C, carbon, double bond, oxygen, carbon, single bond, oxygen, oxygen, hydrogen. Carbon, double bond, oxygen, carbon, single bond, oxygen, oxygen, hydrogen. Ethanoic acid, there are 2 carbons in the molecule, so ethan, and then as it's got the carboxylic acid functional group, oic acid is the name ending. Its molecular formula, C2H4O2, structural formula, CH3COOH. Displayed, we have CH3, C double bond O, C single bond oxygen, oxygen single bond hydrogen. Esters, for instance, methyl ethanoate. Here's the structural displayed structure, CH3, C double bond oxygen, single bond carbon. So this is called methyl ethanoate. Methyl refers to the CH3 group here. Ethanoate, there are 2 carbons in the ethanoate section, 1 carbon, 2 carbons. So this is methyl ethanoate. There are regular questions about structural isomerism. So these are molecules with the same molecular formula. So let's take an example from the previous slide, C4H10. But although they have the same molecular formula, they have differing structures. So C4H10 could be butane, CH3, CH2, CH2, CH3. Here's the displayed structure. Or C4H10 could be methyl propane, CH3, CH, CH3, CH3. So we would draw the structural, or write the structural formula, sorry, in this way, CH3, CH bracket CH3 for the side group, CH3. We would refer to methyl propane as the branched isomer and butane as the straight chain isomer. So branched isomer in that we have a chain of carbons and then off to the side we have another carbon or carbon chain. So that's a branched isomer. So that's an example of structural isomerism. A second example would be position. So if we took C4H8, 4 carbons, 8 hydrogens, so that's an alkene, but-1-ene or but-2-ene. So if I show you but-1-ene, the double bond that must be present in an alkene is positioned between the first and the second carbon. So that's in the chain. So we've got a chain of 4, 1, 2, 3, 4. The double bond is positioned between the first and the second. So that's but-1-ene. What would but-2-ene look like? Can you visualize it? I'm going to show you. First carbon, second carbon, third carbon, fourth carbon. But-2-ene, the double bond is between the second and the third. So this is but-2-ene, starts at the second, the double bond starts at the second carbon. This is but-1-ene, the double bond starts at the first carbon. So these, again, are forms of structural isomerism, frequently asked about in paper 2. So questions about esters frequently include recognizing or naming ester structures. So let's look at an ester, propyl ethanoate. We'll see that the propyl section refers to these 3 carbons here. So that's propyl, carbon, single bond oxygen. So this is the propyl. The ethanoate in blue, CH3C double bond oxygen, carbon, single bond oxygen. So this is the ethanoate section. There's the ethanoate section, and this is propyl. How does that relate to the compounds that were reacted together to make propyl ethanoate? Well, ethanoic acid, CH3C double bond oxygen, single bond oxygen. So that retains the carbon double bond oxygen. So the ethanoic acid becomes the ethanoate part of the ester. Propane 1-ol, well, these 3 carbons here end up here as the propyl section. So naming an ester, we name the alkyl section first, propyl, and then the section containing the carbon double bond oxygen, which comes from the ethanoic acid, as the ethanoate or the alkanoate. So let's have a look at another couple of examples. Methyl ethanoate. What would that structure look like? Well, the methyl would come here, single bond oxygen, and the ethanoate would be the section that contains the carbon, CH3, carbon double bond oxygen, carbon single bond oxygen. So there's the ethanoate. It's got 2 carbons, so ethanoate. The alkyl group has 1 carbon, so it is methyl. Have a look at ethyl methanoate. What do you think its structure would be? Maybe pause the lesson and try drawing the structure, ethyl methanoate. So I'm going to reveal. So where's that naming come from? Well, the methanoate section is the section that contains the carbon double bond oxygen, carbon single bond oxygen. There's only one carbon in that section, so that's methanoate. The alkyl group has 2 carbons, so that's ethyl methanoate. Now, a question that keeps coming up is, what would be the reactants that go to make methyl ethanoate? Remember, we want a carboxylic acid and we want an alcohol. The alcohol provides the alkyl group and the carboxylic acid provides the anoate group. So what acid and what alcohol would be required to make methyl ethanoate? Okay, well, we've got 2 carbons in the ethanoate group, so they come from the carboxylic acid, so that must be ethanoic acid with 2 carbons. The alkyl group is a methyl group. It contains 1 carbon, so that must come from the alcohol with 1 carbon, methanol. If you weren't able to solve that problem, try and give me the acid and the alcohol that reacted to make, or would react to make, ethyl methanoate. Stop the lesson, have a go. Okay, so restarting. The section of the ester that derives from the carboxylic acid, the methanoate section, contains 1 carbon, so that would be methanoic acid. The alkyl group has 2 carbons, ethyl, so that derives from the alcohol, so the alcohol must have had 2 carbons, and that is ethanol. So methanoic acid and ethanol would make ethyl methanoate. Chloroalkanes are not listed in the specification as a homologous series to be known, but they do appear in paper 2 questions as the products of the reaction between alkanes and chlorine. That is substitution reaction. So here is the type of thing: propane, C3H8, plus chlorine. So chlorine substitutes for one of the hydrogens. So we get a product not C3H8 any longer, but C3H7Cl. What's happened to that hydrogen? Well, it's formed hydrogen chloride with the second chlorine atom. So we've got 2 chlorine atoms. One substitutes into the alkane, and we call that chloropropane. And there's a second product, hydrogen chloride. So this is a substitution reaction. Now we need to know about the structures of chloropropane, but I'll throw in one detail here that is often questioned. What is the condition required for that reaction? That reaction only takes place in the presence of ultraviolet light, UV light. That is the energy source. So it doesn't take place in the dark, for example. Now, to get back to the organic molecules, chloropropane shows isomerism, structural isomerism. So if I tell you that one of the isomers has the displayed structure here, and this is called 1-chloropropane. Stop the lesson or pause, think it through. What would be the second possible isomer of C3H7Cl, of chloropropane? If 1-chloropropane exists, what could be the same molecular formula but a different structure, an isomer? Okay, so I hope you've had a think about it. Well, we're going to position the chlorine not on the first carbon in the chain, but the second carbon in the chain. So this is 2-chloropropane. Here the chlorine is on the first carbon of the chain, therefore 1-chloropropane. So this type of isomerism, this condition, this reaction equation, and the idea of a substitution all crop up in paper 2 questions. So obviously you need to practice questions on organic molecules. You'll find them most often placed between question 30 to question 36. Quite a wide range of questions is asked in that section. If you haven't got access to past papers, Google Physics and Maths Tutor, go to their website. They have all the CIE paper 2s you could hope for. If you found the lesson helpful, please recommend it to a friend. Please like, and if at all possible, please subscribe.